Okay, so for the online causal inference seminar today, we will have Professor Lin Liu from Shanghai Jiao University giving a talk. This will be a live talk at the Isaac Newton Institute. We have a live audience here, and some of you are joining us online. Welcome. So for the online participants, please submit your questions using the Q&A box, which is on the bottom of your screen. And the live audience can ask questions directly. Without further ado, then start the seminar.
Okay. Thank you, Qingyuan, for the introduction and the invitation. Hope you can hear me clearly. So today I'm going to talk about the method of moments, U-statistic and high-dimensional generalized linear models when the dimension p is of the same size as the sample size n. So this talk will be based on the following papers, mostly with my students and colleagues. The first paper is a joint work with my students Sihui and Xinbo, and also a colleague Xinzhang from Pfizer. And the second paper is recently put on archive. It's a joint work with Jiao, who recently started postdoc at Tsinghua University, and his PhD advisor Wei Ma from Renmin University of China. And the third one is joint work with my student Xingyu Chen and my longtime collaborator Regression from Harvard. So in this day and age, we're kind of excited about AI. So I'm gonna disappoint you by talking about a very classical topic, which is the generalized linear model. The model cannot be simpler than that. And I recently searched the Google Scholar and found this particular paper with the title as Generalized Linear Model. It's published in GLMs in 1972, but the citation is only 12,000 compared to the deep learning stuff. But that's GLM is still very commonly used in practice. So here's the outline of my talk. I'm gonna first describe the general problem setup, and then I will discuss our approach in linear model as a simplified description, and then I'll come back to the generalized linear model, and then I will show you some numerical experiments. But I'll actually show several numerical experiments throughout the talk, just to motivate our paper or our approach. So here's the very general standard setup in my talk. I'm gonna assume to have access to Ni observations, Yi and Xi. Yi is the scalar outcome or response or label, and Xi is p-dimensional covariates. We assume it's drawn from some common distribution P. The P will be parameterized by the following data generating process. X has mean mu and the covariance sigma. For most of my talk, I'm gonna assume mu is 0. And then I'm gonna assume the mean of y given x, the regression function, is a generalized linear model. So we have a link function phi, and then with beta transpose x. We assume the conditional variance of y given x is hydroscedastic, so we can handle logistic regression or Poisson linear model. So in this talk, I'm going to assume the link function of phi to be monotonically increasing and 3 times differentiable. And in this talk, although it's kind of a standard, a simplified model because we're assuming GLM, we are going to assume some, we are going to consider a sort of difficult regime where the dimension p divided by the sample size n will converge to some constant delta between 0 and infinity. I'm going to allow delta to be 0, but I don't allow delta to be positive infinity. So at most p equal to big O. And the question of interest is to ask how to construct root consistent asymptotic normal estimators of the linear forms of the regression coefficient beta along some given direction v. So we consider inference on v transpose beta or the quadratic form of beta. So beta transpose sigma beta. Sigma is the sigma is the covariance matrix of X, or some other low-dimensional parameters. But in this talk, I'm going to focus on the linear functional or linear form or quadratic form. For most of the talk, I'm going to assume that sigma is known. So in many settings, knowing sigma is not that strong of assumption. One setting is if you have a semi-supervised data set, so you have a lot of x, then you can have a very good estimator of the sigma. Or you are assuming fixed design where the x is fixed, then the sample version of the outer product of x can be viewed as the truth because you are assuming x is fixed. For most of the talk, I'm going to assume the model is correctly specified, so the GLM will be correct in most part of my talk. And so I want to say something more about the parameters. First, the linear form is quite important because it contains special cases like beta j for a certain direction of beta. So in general, people are interested in inference about certain parameter like beta 1, beta 2. The quadratic form is also quite important because it forms the signal to noise ratio, how much x help you predict y. Also, in certain part of my talk, I'm also gonna augment observation from xy to xi, aiy, the triplets, which is kind of familiar to people in causal inference. Here A is a binary treatment, and we are interested in estimating the counterfactual mean of y in the treatment group. Although these problems look simple and standard, there's a rich literature in statistics, applied probability, information theory, and computer science trying to tackle this kind of problem from different angles. Also, there are similar problems in econometrics under the name of many regressive asymptotics or many weak IV. So people, although they are interested in homogeneity setting, but the statistical problem can be very similar. So before I discuss any math, I want to show you just a quick demo about our approach, how it's performed in practice. So here I'm going to consider the following data journey process. So we have sample size n equals to 5,000, and the p equals to less than half of the sample size n, and delta is roughly 0.49. And the x is a normal distribution with mean 0 and the covariance sample and the covariance matrix identity matrix. Here I'm going to generate beta j as IID distribution from a uniform distribution. It's bounded between minus square root 3 over p and the positive square root 3 over p. So it's very small. But the autonorm of beta will be roughly 4 to 1. And y given x, the regression function will be just a logistic regression. It's a Bernoulli random variable with probability xp function beta transpose x. So it's very standard. If you, for any students who have taken stat 101, if you are given this data sets, the first reaction is to fit a GLM using MLE. So if you go to R, fit a GLM with Y and X, and choose the family equal to binomial and select the iteration to very high so that you do not worry about the convergence issue. So numerically, if you should converge, then you should be able to converge. But if in this particular case, you can see that there's a warning message. R says the fitted probability numerically 0 or 1 occurred. So it says it basically tells you that this MLE does not really converge. It's not so surprising because here we choose P to be very large compared to the sample size, roughly half of the sample size. In a recent paper by Manu Kandis and Prakasu, they calculate the if-only condition for the existence of MLE. In this particular simulation setting, we deliberately choose the data journey process so that MLE does not exist. So when R fails to converge, it's not really surprising. But if you insist on reporting the regression coefficients from the R fit, you can look at the regression coefficient estimates from the MLE. Because it's not converging, you can expect that the fit should not be very good. As you can see, the beta 1 is 5.7, but you can observe from this data journey process, the beta should be very close to 0. So there's a lot of there's a large difference between the regression fit and the truth. So if you look at the problem, because P is very large compared to N, the problem is it's not so surprising that you should not use MLE. You can use some other methods like fourth methods to get some regularization. In general, if you do some regularization, you can avoid this kind of numerical instability. So without doing any regularization, here is our output of our approach. The beta 1 is 0.02, beta 2 is minus 0.02, and etc. So if you look at the truth, here's the true betas, beta 1, beta 2. They're not exactly the same, but they're close enough. So as basically using our methods, you can output something quite reasonable. And here I'm using the code from this GitHub link. It's written by my student Lin Liu. So if you go to the website and download our code, you can actually run the program and try this on your own. Here is the snapshot of how these methods actually work using R. So basically, you first initialize some parameters, which will be clear in later part of my talk, and then you plug into this R function. X is the covariates, A is the Y is the response, and then you can do bootstrap to estimate to give a confidence interval of the different betas, and then we'll get some output, and you can try to draw your own conclusion based on output. So that's basically the implementation of our methods. So hopefully I can, so this kind of numerical example give you some motivation to hear my talk. To reveal what we actually do in this approach, let me first simplify the problem even a little more by considering linear models. So first I want to consider a much more simpler model where still we observe Y and Xi. Y is the response, X is the covariates, it's p-dimensional. X is mean zero and the covariance matrix sigma, and the Y is a linear function of X, beta transpose X, and plus some noise. This noise is mean zero and the variance sigma square. The noise, we assume the noise to have light tails, such as Gaussian. We still take the asymptotic regime P over N goes to some constant delta between 0 and infinity. Still are interesting inference on linear form V transpose beta and the quadratic form beta transpose sigma beta. So those are the primary of interest. And again, we assume the sigma is known and the model is correctly specified for most part. So for this kind of problem, there's a long list of works in the literature in the past 10 years. For example, if you are interested in estimating the whole vector beta, then people working in random entry theory and statistical physics, they develop a series of tools to analyze the asymptotic behavior of the error of estimating the whole vector beta using either MLE or regularized MLE. I will not list all the references, but there's a long line of work in the mathematical statistics and the probability theory. For linear form, people have recently started to work on this kind of problem also in proportional asymptotics where P by N goes to a constant. Here are several papers, mostly published in the past 5 or 7 years. And in general, the kind of estimator people proposed are basically trying to generalize the best lasso idea initiated by Professor Jiao and colleagues, and also this paper by John Mard and Montanari in both published in 2014. So for the linear form, what people generally do is first you fit some initial estimate, beta hat initial, using either regularized or unregularized convex loss minimization technique. If you do not do regularization, you can consider least square. So after you get an initial estimator, to construct an estimator for the linear functional, you need to do some devising. It's not so surprising at this moment. So you first have the initial estimator from the lasso or ridge, and then you separate off this kind of inflow function type of bias correction term. Because sigma is known, so you plug in the true sigma inverse, and then xi times, and then the inner product between x and the residual y minus xi transpose beta hat. When in the proportional asymptotics, for the sample size, for the denominator here, you cannot just divide by n. You need to do some degree freedom correction. When you are doing lasso, the degree freedom estimator is basically the number of non-zero coefficients from the lasso output. For ridge, you can also have some closed form formula to plug in the degree freedom correction. So with this kind of construction, you can show that when P over N goes to a constant, this estimator will be a Newton consistent estimator of the true linear function. And for quadratic functional, you can take a very similar approach. You can split the data into two halves. For one half the sample, you can do one device estimator, and for the other half, you can do another device estimator and then plug it in, and then multiply them together to get an estimator of the quadratic functional. And you can show that that estimator can also have is also Newton consistent as not formally disputed and as estimator of the quadratic form. And another idea was recently proposed by in this paper by McGrath and Rajarshi and colleagues. It's published in NeuroIPS. They also they basically employed randomization theory to actually derive the bias formula and then estimate the bias. So there are several different approaches to estimating this quadratic form. And now I want to mention a simpler approach based on moments, because all the previous approach is basically trying to first get some initial estimator and do the bias. But I want to just mention a very simple estimator. For the linear functional, if you know the sigma, I argue that the following estimator is very simple to analyze and it also Newton consistent asymptotic normal. So the estimator goes like this. Because the v direction is known, so just trying to estimate the beta using this particular regression coefficient estimator, the sigma is known, so you plug in the truth. And for the inner product between x, y, you just take the sample average. And it's not really difficult to see that this estimator is a unbiased estimator for the v transpose beta. And also when the dimension p over n goes to a constant, you can directly show that the variance of this estimator is 1 over n, is of order 1 over n. And because of this sum of IID, it's not surprising it's asymptotic normal. We can directly show it's a Newton consistent asymptotic normal estimator of the linear form. And for the quadratic form, it's also not that difficult to show that we can have this second order U-statistic estimator, if sigma is known, to be a Newton consistent estimator for the quadratic functional. Here, you just take the two different pairs, I1 not equals to I2, and then taking the and then compute this particular term yi1 xi1 transpose sigma inverse xi2 yi2. You can directly show that this particular estimator is an unbiased estimator for this quantity yx transpose mean and times sigma inverse takes and then times the mean of xy. And under linear model, this is exactly equal to the quadratic form. And to show this estimator is Newton consistent and asymptotic normal, first you can observe that it's unbiased, and then you need to compute its variance. Because this is a U-statistic, here I'm going to use this UN2 to denote the U-statistic second order U-statistic operator. Because this is U-statistic, you can just do a very simple Hopf decomposition to compute the variance. But the variance have two parts. The first part is coming from the linear components. It's of order 1 over n. It's like behaving like a sample average. And there's another second order degenerate part, which is of order PON squared. But if you assume P over n goes to a constant, then PON squared is still converging to 1 over n. So again, the variance of this second order U-statistic estimator is of order 1 over n. In terms of the asymptotic normality, we can use martingale CLT to show that the Newton scale difference between our estimator minus the truth will convert to some normal distribution with mean 0 and some variance U squared. And under some regular condition, I'm not going into details in this talk. And some remarks about this particular second order U-statistic estimator. First is there's no sample splitting involved. You just compute the second order U-statistic from the whole sample, and there's no hyperparameter tuning. Unlike using Lasso or Ridge, you have to tune the lambda parameter using cross-validation eventually. But here we do not use this any. We don't need to tune any tuning. We do not need to tune this hyperparameter. Also want to mention that this particular estimator of the quadratic functional is actually a special case of higher order int functions initiated by Jamie Robbins and Art Vandermark and colleagues under this particular linear model. It's just a special case of that. And in higher order int functions, the variance structure 1 over n plus PON squared is actually the key for backstreet reduction without inflating variance too much. And the CLT can be proved by using martingale CLT as well in the higher order int function literature, using, for example, this paper, this 1992 paper by Bhattacharya and Ghosh. So basically, all the tools are already there. So please feel free to interrupt me anytime during talk. Just want to. So if there's no question about this particular quadratic functional or quadratic form in the linear model, I want to take a brief segue to consider a slightly different problem, but still quite similar in spirit to that particular problem. So this problem is actually related to covariate adjustment in randomized experiments with linear working models. So here I'm going to consider this triplets. So we have xi, p-dimensional, and ai, yi. Here I'm going to assume the treatment sum ai is a Bernoulli with probability pi. So it's in randomized experiments, you basically randomize the people into treatment group, control group without any dependence on x, and the pi can be 1/2, so ai will be independent from x in this particular design. And in this part, I'm going to assume fixed design where the xi's are fixed, so there's no randomness xi. And there's no assumption on the conditional mean of y given x and a. So for the outcome regression model, we do not assume any particular structure. And the goal is still to construct a Newton consistent asymptotic normal estimator of the counterfactual mean of y in the treatment group. This is very commonly this is a very common problem of interest in randomized experiments. And because we are randomized, there's a very natural and simple unadjusted estimator, which is already Newton consistent asymptotic normal, which is the following estimator. In the RCT literature, people call that unadjusted estimator. But if you are working in causal inference, it's basically IPW estimator. So it's basically AI, YI divided by the treatment sample probability pi and then taking the sample average. But people already know that this particular unadjusted estimator can be suboptimal in terms of the variance, because for this estimator, you are not using any information of the covariates. In nowadays clinical trial, people actually can collect a high dimensional covariates just to improve efficiency. So it's kind of already known in the literature that efficiency or the variance can be improved by fitting a linear working outcome model and using the AIPW estimator when the dimension p is much less than Newton. So here I'm just list a very incomplete list of references, like the paper by Mr. Lin, and then my paper Weima, and also a paper by Ting Ye and colleagues. Also, I think this paper, Qing Yuan is also one of the co-author of this paper. And there's a recent paper by Jiao et al. Published in GLE. They're basically trying to show that this IPW estimator is Newton consistent asymptotic normal as long as the dimension p of the covariates is much less than the square root of sample size. So here is the form of this adjusted estimator. Basically, it's an AIPW estimator, but using a linear outcome working model. As you can see here, this part, the red term, is basically trying to do a linear regression between the IPW weights of the outcome, the transform outcome, onto the covariates. So this is a very simple version of the IPW estimator. So basically, you can show that as long as the dimension p is much less than the sample size, this estimator should be Newton consistent asymptotic normal and can improve efficiency compared to unadjusted estimator. But how about what if we want to go beyond p less than Newton? What if the dimension p is actually greater than or up to than Newton up to constant? Then let me rearrange the adjusted estimator a little bit. So here, what I'm doing is basically trying to move this summation over the j indices to the left-hand side, so that you can see that for this standard adjusted estimator is basically a V statistic. So it's summation over I equals 1 to n and summation over j equals 1 to n. Then I just do some manipulation of this quantity. I break this V statistic into two parts. The green part is a U statistic. The red part is the diagonal summation. So it's a summing over all the I, j equal to each other. If you focus on the U statistic term, the green term, you can immediately see that this has mean 0. If you divide by n times n minus 1, but the bias is also small 1 over n. The variance of order 1 over n plus p1 squared, we have to show that, we have seen that in the quadratic form example. We can just follow the same kind of calculation, the proof strategy to show the variance order is 1 over n plus p1 squared. And you can show it's asymptotic normal using Martin-Gauss LT. even the fixed design, so basically I'm assuming the sigma hat is known, so there's no randomness of X. So when you compare the bias of the estimator, you do not have to try to control the bias of estimating sigma hat after estimating the sigma inverse by sigma hat. The right term, this diagonal part, still has mean of order P over N. So once the P is much greater than the square root of sample size, this right term will incur a bias of order 1 over root n or larger. So this standard estimator will fail to be root n consistent and asymptotic normal as long as you have dimension P is sufficiently large compared to the sample size. Of course, based on this algebraic manipulation, there's a simple fix. Just remove the red part and using U-statistic instead. And this is exactly what people have been doing when they consider the data to be a randomization based, to be a final population data, where both the X and potential outcome are fixed. So I just listed several papers. One is by Chang et al. Published in Econometrica, and then Lu et al. Published in the Annals in last year, and also one of our own papers, which is our archive in 2024. So basically, this is the estimator we proposed. So tau hat is basically IPW estimator or the unadjusted estimator minus the augmented term, but removing the diagonal summation. So we directly just use the U-statistic to estimate the augmented term. You can show that
the sigma hat that you know, there's a sigma hat.
Yeah, there's a sigma hat.
And so
we are using the sample version to estimate.
Just the sample
version, because here I'm assuming P is still less than N.
You assuming?
So P is less than N.
Okay.
Yeah. And also in their paper, they are assuming the fixed design setting. So there's no randomness X. So the sigma hat is the truth for them. When you look at the bias, you do not need to control the bias between sigma hat inverse minus sigma inverse in a fixed design setting.
I thought in this paper on debiasing, I'm not a great expert, that estimating the variance was the hard part, and you say you just take the empirical.
So here I'm just taking the P proportional to N and the P less than for the beginning of the talk. Later in the end, I will consider P bigger than what we can do in that case. But I will not consider the P much greater than that case. So it's the high dimensional, but in the kind of moderate high dimensional case. So it's not really the ultra high dimensional. So it's kind of very similar to what higher order function has been doing in that regime. So this is the estimator we are proposing. It's a U-statistic-based estimator. I haven't shown that. I've shown that this tau hat is root consistent as a normal. It never hurts and sometimes improve efficiency as long as the P is small. And when the P is proportional to the sample size, the variance, there can be certain scenario where you can observe some variance inflation. But when P is small, there's no problem. And in our own paper, we actually point out that this tau hat is again a special case of higher order infinite function estimator of tau under the special case of randomized experiments and the fixed design. Basically correspond to knowing the true treatment sample probability and knowing the true current matrix. And in this paper with Yu Jiagu and Wei Ma and myself, we contrast a very similar U-statistic adjusted estimator tau hat for quadratic design, which is more commonly employed in clinical trials. We also show that this tau hat is root consistent and as a normal and improved efficiency as long as P equal to small n in the superpopulation setting. So here we are considering the much more difficult setting for analysis because the proof becomes much more involved as we need to control the difference between estimating the current matrix sigma using the sample versus the true sigma under this P equal to O n setting. We also do not do sample splitting. We are using the same sample to estimate the current matrix.
But you do not need conditions to be able to get a rate on that.
We need a condition. We need, for example, X to have bounded second moment, and the inner product of X transpose X to be of order P. So that kind of condition we still need.
But nothing on the inverse, say?
Well, we assume P is less than
sparsity?
No sparsity. We will assume P is smaller. So the dimension is much smaller than sample size. So there's no sparsity needed in this case.
dimension is smaller than sample size.
Right. So P is small.
Does that mean with sparsity, the dimension is smaller?
But here I'm not going to assume the sigma inverse have any sparse structure.
P is just the number of, not the number of
Exactly.
non-zero,
Yeah,
but
P is
just the number
of bases or number of covariates.
Yeah. And how small does it have to be then? Up
to show unbiasedness, we do not need. We only need P to be. Actually, for unbiasedness, we do not need any assumption on P as long as sigma is invertible. For variance improvement, we need P to be small of sample size.
But the comparison to the debiasing in the Lasso case is not quite fair.
Yeah, it's not.
The P is
I'm not
bigger than the N, and then you assume sparsity of the non-zero coefficients.
I'm not trying
to work hard.
Yeah, exactly. Yeah. Here I'm considering this a moderate high dimensional setting. I want to mention that recently in this 2025 paper by Alberto Abadi and colleagues, they, instead of using the sample approximation to estimate the inverse, they replaced this particular estimator by rate numbers for numerical stability in the better finite sample performance. I want to mention that in the implementation, we actually use the generalized inverse also for numerical stability issues. One word about the implementation, we now have an R package called Harvard function car, because we're using Harvard function ideas and then plug into and then apply for quadratic adaptive randomization. And my hope is that this package can serve as a supplement to the popular packages such as Robin car for co-adjustment in RCT when the dimension P is large relative to the sample size. You can find out our R package from this GitHub link. In this package, we cover linear working models under the simple randomization and the quadratic adaptive randomization, and under both finite population and superpopulation models. So for the variance estimator, we have both. We have variance estimator both for the finite population and superpopulation settings. We also implement methods using GLM as a working model under simple randomization and superpopulation model. It's already in the package, but for the paper will be released soon, hopefully in 1 or 2 weeks.
So then the question from online, why do you use martingale CLT?
For U-statistic, if you want to show the asymptotic normality for U-statistic, you need to use the martingale CLT to show that. Yes. And I want to show you some simulation results. So here I'm considered a Y is a binary outcome. It's a logistic regression. It's a logistic function with some nonlinear transformation of X. So that's how we generate Y. And the A is the treatment assignment is randomized. So it's with equal probability. And we are comparing both the unadjusted estimator, is the red part, and the standard adjusted estimator, which is the OLS, the yellow curve, and our U-statistic-based estimator, which is the blue curve. The green curve, I call that oracle because here I'm considering a superpopulation model. So we have some underlying true sigma. Here, the true sigma is identity matrix. So I'm also plotting that particular infeasible estimator in the simulation. As you can see from this plot, once the P/N ratio goes to it's getting large, the standard estimator will have large bias. Even the variance will become very large after a certain ratio between P and N. But for our own estimator, the blue curve, the bias is always small. The variance is always smaller than the unadjusted estimator, at least up to P/N goes to 0.8. And also the coverage probability is very close to the nominal level, 0.95. But for the standard estimator, it starts to fail to cover at the nominal level once the ratio between P and N goes beyond 0.1. So that's the simulation illustration. So any question up to this point? So now let me go back to the original problem. How about GLMs? If we assume the model is the generalized linear model, what can we do? Again, there's a long list of works for logistic regression and other type of GLM when P/N goes to a constant. Here I also list several papers along this direction. The state-of-the-art estimator is basically trying to do some fancier debiasing. both in the moderate dimension and in the ultra high dimension setting. In the moderate dimension, people can just do ridge, but still need to do some degree freedom correction. So I think in the most general form of this kind of device estimator was proposed in this paper by Professor Pierre Belek, published in the Annals in 2025. But for this kind of device estimator, to our knowledge, it was first appeared in for logistically rich regression in Park-Yasu's thesis. So here's the device estimator. It's very similar to the linear case, except that the degree freedom correction in here, you need to derive that from a system physical equation using the technique called the technique called approximate message passing. So this machinery, if you need to master this machinery to be able to derive what kind of degree freedom correction you need to use to get this device estimator to be written consistent and acceptance normal under the pure and Goldstone constant setting. And the analysis is also quite involved. It requires randomization theory and good knowledge about AMP techniques. So then our question is whether we can do a similar trick in the linear model setting, also for the generalized linear model setting. So for GLM, here we are considering the regression function y given x is the monotone transformation of beta transpose x. Phi is monotonically increasing and 3 times differentiable. If we assume the regression function is the GLM, many nice properties of the linearity are lost. But it turns out that there's still enough structure to leverage using Stats lemma or Gaussian integration by parts if we assume the design x to have a normal distribution. So here I'm considering a simple setting where x is normally distributed with mean 0 and current sigma. So we steal from this object, where in the linear model, we can estimate this object unbiasedly using second-order U-statistics. However, to connect this object to quadratic form, the parameter of interest, is not as easy as in the linear model case. Here, we just first do a conditional, iterative expectation. We replace y by its conditional mean, phi of beta transpose x. At this point, it's still not too clear what to do. But because we are assuming Gaussian, we can do a Stat lemma. We can replace the mean of this linear mean of conditional mean of y given x and x by phi prime, the derivative of phi, the derivative of the Lin function, still beta transpose x, and then beta transpose sigma. And then we can do the same thing for this quantity. And after some algebra, you can see that this sigma and sigma inverse cancel. So this quantity can be written as the quadratic form multiplied the second by the square of the first moments of the first derivative of beta transpose x. But remember, x is Gaussian, so beta transpose x is still mean 0 with variance of the quadratic form. So eventually, we can still write down the object on the left-hand side as some nonlinear transformation of the quadratic form of beta. Although this nonlinear transformation, I call that psi, is nonlinear, but we can show that this is a monotone and also differentiable. So it's basically global diffeomorphism. So basically it means that the inverse map also exists, is also differentiable. So with that kind of observation, what we can do is we can first, using the same second-order U-statistic to estimate the object on the left-hand side, and then plug in to the inverse map of this nonlinear transformation psi to get an estimator of the quadratic form, beta's transpose sigma beta. And by similar trick, we can also construct an estimator for the linear form of beta along some known directivity. So this, so the previous estimator basically assumed x has mean 0, and we know x has mean 0. Now I want to generalize this trick a little bit more. I want to assume x has mean mu is not equal to 0, and the current sigma. Now it's not as straightforward to identify or to estimate the quadratic form beta using the same trick. But it turns out that we can still construct two system equations by bringing in the mean of y into the picture. So here on the left-hand side, we have mean of y and some objects very similar to that object we can estimate by U-statistic unbiasedly. And on the right-hand side, we can again write it as some nonlinear transformation of the quadratic form of beta and also the linear form of beta along the direction of mu. Mu is the mean of x. So even though one equation is not enough, we can construct two equations to use the same trick. So basically, we now have a nonlinear transformation psi. It's a mapping from a linear form beta transpose mu and the quadratic form beta transpose sigma beta to this left-hand side, which can be unbiased estimated by second-order U-statistic. So here, all the moments on the left-hand side of this equation can be unbiased estimated by first and second-order U-statistic because mean of y can be estimated by sample mean of y, assuming sigma is known. And then if you estimate the left-hand side and then plug into the inverse map of the linear transformation, you can get some get the estimator of beta transpose mu and the quadratic form of beta. So the proof is not that difficult. So first, you basically show that. So basically, you can also show that this nonlinear map is a global diffeomorphism. The proof is not that difficult. So you basically first show that the determinant of the Jacobian of this nonlinear transformation, this nonlinear map, is always bigger than 0, and then you show that this nonlinear map psi is a proper map, which basically means that its input, when its input goes to the boundary, its output also goes to boundary. And then you can employ the Hadamard global inverse function theorem to show that this local diffeomorphism is actually a global diffeomorphism. So eventually it's a bijective map, and both the inverse and the forward map is differentiable. So basically you can then estimate the linear form and the quadratic form using the second order U-statistic and plug into the inverse map to get a root and consistent asymptotic estimator of these two parameters. The proof is also not hard, not difficult. You basically show the root and consistent asymptotic normal for the U-statistic, and then because this nonlinear map is a global diffeomorphism, you can use the auto method to show the root and can property of the prime of interest, which is the beta transform mu and the quadratic form of beta. I want to mention that there's a paper in 2023 by Sawaya et al. They only use the mean of y to estimate a quadratic form beta in binary regression, but they require the link function to be asymmetric around 0.5. So it kind of includes logistic regression or probability regression in that sense. But we allow those more commonly used link functions. Of course, all the previous results is based on the Gaussian assumption of the design. It's not really satisfying for statisticians in general. In the AMP literature, universality has been established beyond Gaussian design. And we want to also ask the question, what about for estimating linear or quadratic forms? And without Gaussian entity, it turns out that under certain structure on the betas, we still can have we can still construct an can estimator for the beta transpose mu and for the linear form of beta along the direction mu and the quadratic form beta. So here's our theorem. We show that if you assume the beta are sufficiently delocalized, basically it's saying that all the direction of beta are like an IID draw from some common law from some common distribution indexed by this small beta. And if x is the sigma half times z plus mu, where z is p-dimensional IID coordinates with mean zero invariance, we can still use the same equation to identify the linear form of beta along the direction mu and the quadratic form beta, up to some error. The error is of order n to the minus 3/4, so you don't have to worry about the actual bias in this particular problem because it's smaller than 1/√n. And the proof, this lemma follows directly from the Lindenberg universality principle, is actually in Chatterjee's paper. And the intuition is basically saying that the beta transpose x, when the dimension is sufficiently high, mimics some of PID random variables. So can, even though x is not normal, the beta transpose x can still be approximately well binomial distribution. We also have something under the case where the sigma is unknown, but the p is less than n. Here we consider a lazy solution. We still assume the axis Gaussian distribution with mean 0 with variance sigma. Here we just use the sample covariance matrix and take an inverse. We do some sample splitting. Because we're assuming Gaussian, we know the inverse sample covariance matrix is inverse Richard. So we can just directly do some rescaling of the second order statistic to show that it's still an unbiased estimator of this particular object. And from this, we can show that we can construct the unbiased and the root consistent estimator of the linear form and correct form of betas, even if we do not know sigma, but p is less than n, so that the covariance matrix the sample covariance matrix can be invertible. When p is bigger than n, it turns out that we can use a technique. I think based on our knowledge, is first proposed in this paper by Tong and Valiant, published in Neuroips in 2018. We also want to thank Professor Nicholas Berzellen for bringing this reference to us. So basically, in that paper, they approximate the inverse of the sigma by this polynomial transformation of sigma up to a very high degree of polynomial. So in that paper, they use Chebyshev polynomial, but other polynomials also possible. So basically, you can take j equal to some square root log n, and then estimating this polynomial of sigma using higher order U-statistic. Again, the form is very similar to the higher order input function estimator when you let the order to go higher and higher. And with this kind of construction, you can show that at least you can have a consistent estimator of the linear form, the correct form in a generalized linear model. At this point, I want to just give you some advertisement that we recently we developed a software for computing higher order U-statistics with two of my students, Xingyu and Ruiqi. We leverage techniques from computational mathematics, also used in tensor networks. We basically develop Python-based software for computing higher order U-statistics up to order 7 or 8. We now have a R interface for this package. And if you want to implement the higher order if functions, you can also go to this web page to get the code, and please feel free to try it on your own. And we're also eager to hear any feedback on our code. But we can basically using this method to construct to estimate this particular higher order polynomial at least up to order 7. Finally, I want to just mention a couple of other applications of our approach. I want to first jump over these 2 slides. So first, in our approach, we can also handle the problem of estimating the mean of y and the Bayesian random. It's basically isomorphic to the problem of causal inference for estimating the trimming effect and the unconfoundedness. And you can also use our approach to estimate the bilinear form of mean of t given a given x and the mean of y given x. So it's basically the correspond to the expected conditional covariance parameter. It can be used for testing conditional independence between t and y given x. You can also estimate the parameter tau in this partial linear model. Well, it's not partial linear model, but you can think about the first coordinate of this linear model as the parameter of interest and the rest of the nuisance parameter. So all these models can be handled using this U-statistic-based approach. And I also want to mention that our proposed estimator by no means try to replace the biasing approach. We want to just give another alternative procedure to make to basically leverage the model structure more. So because the model assumes Gaussian in general in the literature, want to leverage whether this how far this model assumption can get us. So our approach is kind of different from the device literature. I want to mention that our proposed estimator may not be really optimal because the lower bounds is not really established yet under the proportional asymptotics. So we have no idea whether our proposed estimator or the device estimator is optimal in any sense. So this is still some open question. And for inference of device estimator, one often needs to solve these AMP-based fixed point equations, and there's some unknown parameters. For those unknown parameters, you can also use our approach to estimate those unknown parameters, and then use the AMP type of analysis to get confidence interval or bias correction. So our approach can be used as a warm start of the more advanced devised estimator. Finally, I want to show you some numerical results. So this is the logistic regression. Alpha is high dimensional. Still the uniform distribution between very small lower and upper bound. X is Gaussian with mean zero and identity matrix, identity convergence matrix. The dashed line here is our estimator. As you can see, by changing the sample size and the p-run here, we are fixing p-run to be a half. By changing increasing the sample size, the root bias is basically a constant for our estimator. And the colored line, colored solid lines are the device estimator based on Professor Belik's paper. It's involves some regularized parameter. It involves some tuning parameter lambda. So with different lambda, you have different bias and variance. But as you can see, both the bias and variance are very similar to their. Our estimator have very similar root and bias and variance compared to their devised estimator for estimating quadratic functionals. This is a Gaussian design. We also have the random marker design, but again, we assume the alpha is dense so that the universality can kick in. Even though the X is now Gaussian, we can still use the Gaussian theory to estimate the linear functional, quadratic functional. So here for the alpha 1, alpha 100, we have root and bias. The dashed line is our estimator. The solid colored lines are the device estimator. Because the tuning parameter can be different, they have different values. So we have, again, our bias and the variance are very similar to theirs. Of course, we only have one value that can explore different range of lambda to have better bias variance trade-off. We also compare our procedure to this paper by Michael Sonatano and Martin Wainwright. They also do this device lasso type of estimator using AMP to get the device formula. We just do our own methods moments using U-statistic, but instead of estimating 2 equations, we need to estimate, I think there are 7 U-statistic we need to estimate. But eventually, this is our performance. The root and bias is the dashed line. The color solid line is their AMP-based methods. The variance is also quite similar between our methods and their device version. And similarly for the non-Gaussian case. So to summarize, in this paper in this work, I basically show that in the moderate high dimensional setting where the P is of order big O(n), we can, for linear model and the generalized linear model, we can always construct some mapping between objects which can be estimated by U-statistics motivated by the higher order function technique, and the linear and quadratic forms of the regression parameter beta, which can be of scientific interest in practice. So you can use the techniques that people develop in the U-statistical higher order function literature to estimate those quantities. And our methods can be used to estimate some unknown parameters in the AMP state evolution for constructing confidence intervals. So you can view our procedure as some initial or warm-up step of their more advanced techniques. And there's some open-ended question. For example, what if your design is non-Gaussian and the universality does not hold? We do not have any solution for that kind of problem. We do not have any solution for that kind of problem yet. And in this part, in these papers, we basically focus on linear form and the quadratic form beta. So basically correspond to linear and the quadratic functional beta. How about you want to estimate or draw inference on some low degree polynomial beta, like third order polynomial beta or higher order polynomial beta? We do not have a good answer yet, but that's something that can be of interest to study. And in this approach, we basically try to numerically solve this inverse map. there could be some better numerical algorithms. We for the current implementation, we just do the default R software. We just use the default R package to do this inverting to do this inversion. But there could be some better methods for this numerical inversion, which can be used for this kind of procedure. And then finally, what is the optimal estimator in this kind of setting? Our conjecture is that our moment-based estimator is not necessarily optimal, but we do not really know the lower bounds, and so in the current setting we do not have a tool to compare whether our estimator achieves some variance bound or not. So that's still some open-ended question. So I'll just stop here and thank you for listening.
Thank you very much, Lin. Are there any questions from the room?
Let's do slide 41. So is there reason the biases moving opposite direction compared to the device methods?
Yeah, that's we do not know. Just
Maybe the device isn't much.
but the bias is still quite low for them because it's already multiplied by root sample size. So the bias is already pretty low. The absolute bias is very low.
So the simulation setting, you generate a lot of small alphas, but all the same magnitude.
Yeah.
Is that the only thing that's of interest, or would it also be interesting that some alphas are actually big and that it's more varied?
Right. So for Gaussian, for Gaussian case, that different kind of beta will not validate our assumption. But this kind of localization will be needed will access non-Gaussian, so that you need to use some universality to show that even it's under non-Gaussian, the beta transpose X still can be approximated by a Gaussian random variable. In that case, it's a IID generation can be important. For example, in this Rademacher case, if we do a sparse alpha, some are non-zero and most are zero, then our method fails, but also the bias method also fails. So in that kind of setting, we do not really know what's the best answer yet.
In the general linear.
In the general linear.
Also in the Gaussian. The linear.
No, not Gaussian, non-Gaussian case.
And what is difficult about getting efficiency? Why is it hard to
So
see
when we do this,
I mean, not the methods, but to see what the bound is. Why is it?
So at least when we do this Bayesian argument, what we got is still the fixed dimension type of variance. We do not have this variance inflation, which have been observed in the proportional asymptotic literature. So we're still struggling to get that actual term. So the bound we got is still the standard efficiency lower bound type of results using the Bayesian argument.
I think we will call it there. There are a few questions on the chat, but I will ask you to answer them offline.
Okay.
Okay. Thank you very much.
The map is invertible, and both the forward map and the reverse map are differentiable. That's good. What kind of polynomial could replace the Chebyshev? So in the ongoing work, actually we are exploring polynomial like Bell polynomials. So as long as the approximation error of the polynomial approximating the inverse map, approximating this reciprocal function 1/x. If at order j or at degree j, if the approximation error is e to the minus some factor of j, then that kind of polynomial can be used. So we only need that kind of assumption. So any polynomial satisfy that assumption can work in principle. And I think Bell polynomial is one of those polynomial you can explore. And the minimax approach help to come to optimality. So basically, in our previous exploration, we have used this minimax approach to. So basically, we are using a Bayesian argument. Bayesian argument is give you some lower bound of minimax lower bound. But we do not get the usual variance simulation that people observe in the proportional asymptotics. So that's why I said this is still open question. So I'm not sure whether I answered this question or not. And for Richard's question, design matrix come from factorial design. Does Gaussian universality still apply? So based on our theorem, I do not think it's directly applicable because we need the Gaussian matrix to have the structure of sigma 1/2 multiplied by some ID random vector plus some mean shift. So if your matrix cannot be written as that form, then this kind of theory cannot be directly, it's not directly applicable. But it's possible to use any particular structure in your particular matrix to also get some universal result. That I'm not sure. But using our current theory, we cannot handle this kind of matrix yet. I'm not sure whether using some other technique you can get around this issue. And also, even if your matrix satisfies these constraints, we still need, just as Art commented, we still need this regression coefficient to be delocalized or sufficiently similar to IID generated betas to make sure the Gaussian analytic kicks in. That's the short answer. Oh, I understand.
There's the last one.
Okay. In our analysis, there's no AMP involved. So that's why I mentioned the analysis is very simple. We just use standard computation to analyze the variance and then martingale CLT to show the U-statistic is normally distributed. That's it. No AMP involved. So it's kind of simple to analyze.
Thank you very much again, Lin.
Thank you.
I will close the recording.